For billions of years, light has been our only witness to the universe beyond Earth. It has carried the glow of distant galaxies, the afterglow of the Big Bang, and the faint reflections of worlds we will never visit. Every photon that reaches your eyes right now has traveled an incredible journey. Some left their source just 8 minutes ago from our sun. Others began their voyage when the universe was young, carrying messages from galaxies so distant that we see them as they were billions of years in the past. Think about this for a moment. The light hitting your retina right now has stories to tell. It might have bounced off a cloud this morning, or traveled for eons through the vacuum of space, dodging asteroids and bending around massive stars. Each beam carries information about where it has been, encoded in its color, its intensity, and the way it vibrates through space. But here is a question that pushes the boundaries of imagination. What if light did not just carry energy and color? What if every single photon could remember every step of its journey? What if light had a perfect memory of every interaction, every collision, every moment since it was born? Imagine catching a ray of sunlight and being able to read its complete biography. You could see exactly which atoms in the sun's core created it 13 billion years ago, watch it fight its way through layers of plasma, witness its final escape from the solar surface, and follow its path through space until it landed on your skin. You could replay its entire life story like watching a movie in reverse. This is not just science fiction daydreaming. This question touches on some of the deepest mysteries in physics. How does information travel through the universe? What counts as memory in the quantum world? And why does nature seem to forget most of what happens, keeping only fragments of the past? If photons could remember everything, we would have access to the ultimate cosmic archive. Every beam of light would be a time machine, carrying perfect records of events that happened millions, billions, or even trillions of years ago. We could watch the formation of the first stars, see how planets were born, and witness moments in cosmic history that we can now only imagine. But the story gets even stranger when you realize that light already does remember, just not in the way we might expect. Every photon carries clues about its past, written in a language that physicists are still learning to read. The challenge is understanding what those clues can tell us about the nature of reality itself. Would we, for the first time, have the ability to replay the universe itself? The answer might change everything we think we know about time, space, and the cosmic story that connects us all. To imagine light with memory, we need to understand how light works today and how it already carries fragments of history. The story of light is one of the most beautiful and mysterious tales in all of physics, and it begins with a simple question that puzzled scientists for centuries. What exactly is light? For most of human history, light seemed like magic. It appeared instantly, traveled faster than anything else we knew, and somehow let us see the world around us. Ancient philosophers thought light shot out from our eyes, like invisible fingers, reaching out to touch objects and bring back information. Others believed that objects themselves sent out tiny copies of themselves that flew through the air and landed on our vision. The Greeks debated whether vision worked by emission or by reception, never imagining that the truth would turn out to be far stranger than either possibility. The first real breakthrough came in the 1600s, when scientists began to realize that light behaves like a wave. Christian Huygens, working in the Netherlands, proposed that light spreads through space like ripples on a pond. Just as dropping a stone creates circular waves that expand outward from the point of impact, light sources seem to create waves that spread in all directions through some invisible medium. But what was this medium? Scientists called it the luminiferous ether, an invisible substance that they imagined filled all of space. Light waves, they thought, were vibrations in this ether, just as sound waves are vibrations in air. The ether had to have remarkable properties to carry light at such incredible speeds, while remaining completely undetectable to our senses. The wave theory explained many puzzling observations. When light passes through narrow slits, it creates interference patterns with bright and dark bands, just like water waves do when they meet and either reinforce or cancel each other. Light could also be diffracted around obstacles, bending slightly into shadows, in a way that made sense if light were indeed a wave phenomenon. Then came James Clerk Maxwell, a Scottish physicist who changed everything in the 1860s when he wrote down 4 elegant equations that describe how electric and magnetic fields dance together. These Maxwell equations were like a Rosetta Stone for understanding light. They revealed that light is an electromagnetic wave where electric and magnetic fields chase each other through space in an eternal cosmic dance. Here is how it works. An oscillating electric field creates a changing magnetic field, which in turn creates a changing electric field, and so on. These two fields support each other as they race through space at exactly 299,792,458 meters per second. This speed, which we call the speed of light, turned out to be one of the most important constants in the universe. Maxwell's equations also predicted that electromagnetic waves could exist at many different frequencies. Visible light, with frequencies between 400 and 750 trillion oscillations per second, represents just a tiny slice of the electromagnetic spectrum. Radio waves oscillate much more slowly, while X-rays and gamma rays oscillate much faster. All of these different types of radiation are fundamentally the same phenomenon, just at different frequencies. The success of Maxwell's theory seemed to settle the question. Light was clearly a wave, but then came one of the most shocking discoveries in the history of science. In 1900, Max Planck was studying how hot objects glow when he discovered that energy comes in discrete packets, or quanta. 5 years later, Albert Einstein used this idea to explain the photoelectric effect, showing that light also behaves like particles. These particles, which we now call photons, carry discrete packets of energy. The energy of each photon depends on the frequency of the light according to Planck's constant, one of the fundamental constants of nature. High-frequency light carries high-energy photons, while low-frequency light carries low-energy photons. This means that blue light, with its high frequency, packs more energy per photon than red light. This wave-particle duality means that light is both a continuous wave and a collection of individual particles, depending on how you choose to observe it. It sounds impossible, and it violated every intuition that physicists had developed about how nature works. But quantum mechanics teaches us that the universe is far stranger than our everyday experience suggests. Light can interfere with itself like a wave, but it also hits detectors like individual particles. Each photon is like a tiny messenger carrying information encoded in its properties. The most obvious property is energy, which determines the color we see. When your eyes detect photons, they are essentially counting these energy packets and interpreting their values as different colors. Red photons carry about 1.8 electron volts of energy, while blue photons carry about 2.7 electron volts. This might not sound like much, but remember that even a dim light bulb produces trillions upon trillions of photons every second. But photons carry more than just energy. They also have a property called polarization, which describes how the electromagnetic field is oriented as it travels through space. Think of it like the way a jump rope moves when two people shake it. The rope can wiggle up and down, side to side, or in diagonal directions. Similarly, the electric field of light can oscillate in different directions perpendicular to the direction of travel. Most natural light is unpolarized, meaning it contains photons with random polarization directions all mixed together. But certain processes can create polarized light. When sunlight reflects off water or glass at certain angles, it becomes partially polarized. This is why polarized sunglasses can reduce glare. They block photons with certain polarization orientations, while letting others through. There is also something called phase, which is like the rhythm or timing of the wave. Two photons with the same energy and polarization can still be out of step with each other, like two dancers doing the same moves but starting at different times. This phase information is incredibly delicate and can be easily scrambled by interactions with the environment. When light travels through different materials or encounters obstacles, the phase relationships between photons can change in complex ways. Photons also carry momentum, even though they have no mass. This momentum is proportional to the photon's energy divided by the speed of light. It is tiny for individual photons, but light pressure from billions of photons can actually push on objects. This is how solar sails work in space, using the momentum of sunlight to propel spacecraft without fuel. When physicists today talk about photons, they use a theory called quantum electrodynamics, or QED for short. This theory, developed by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga in the 1940s, describes how photons interact with matter at the smallest scales. According to QED, photons are excitations of the electromagnetic field, like notes played on a cosmic piano that fills all of space. In this view, what we think of as empty space is actually filled with quantum fields that can vibrate in different ways. A photon is a particular type of vibration in the electromagnetic field, a wave packet of energy that can travel from one place to another. These field vibrations can be created when electrons jump between energy levels in atoms, or destroyed when they are absorbed by matter and transfer their energy to other particles. QED also tells us about virtual photons, which are quantum fluctuations that mediate forces between charged particles. When two electrons repel each other, they do so by exchanging virtual photons. These are not real photons that you could detect with instruments, but they represent the quantum mechanical way that electromagnetic forces operate at the smallest scales. Here is the crucial point for our story about memory. In standard physics, photons have no awareness and no internal structure that could store detailed information about their past. They are not little libraries carrying complete records of every interaction they have experienced. Instead, they are simple quanta of the electromagnetic field, each one described by just a few basic properties like energy, momentum, polarization, and phase. This means that when a photon reaches your eye after traveling from a distant star, it does not carry a detailed log of every dust grain it encountered, every gravitational field it felt, or every magnetic field it passed through. The photon simply carries its final state, which has been shaped and modified by all those interactions, but does not explicitly record them in any retrievable form. Think of it like a letter that gets passed from person to person. Each person might change the letter slightly, maybe smudging the ink or creasing the paper, but the letter does not keep a record of who handled it or what they did to it. You can see the final result of all those interactions, but you cannot replay the sequence of events that led to the letter's current condition. Yet even without perfect memory, light does carry clues about its history, and these clues have revolutionized our understanding of the universe. The story is written in subtle changes to the photon's properties that occur during its journey through space and time. Learning to read these clues has been one of the greatest achievements of modern astronomy. Consider redshift, one of the most important discoveries in astronomy. When light travels through expanding space, its wavelength gets stretched out, making it appear redder than when it was first emitted. This happens because space itself is expanding, carrying the light along with it, and stretching out the wave crests as they travel. The amount of redshift tells us how far the light has traveled and how much the universe has expanded since the photon began its journey. It is like a cosmic odometer, recording the distance traveled through space and time. The discovery of cosmic redshift in the 1920s by Edwin Hubble completely changed our picture of the universe. By measuring the redshift of distant galaxies, Hubble showed that the universe is expanding and that more distant galaxies are moving away from us faster than nearby ones. This led to the realization that the universe had a beginning, what we now call the Big Bang, and that it has been growing and cooling ever since. Polarization changes also encode history. When light scatters off dust particles or electrons in space, its polarization can be rotated or modified in characteristic ways. The amount and direction of these changes depend on the properties of the scattering material and the geometry of the interaction. By studying polarization changes, astronomers can map the distribution of matter between distant galaxies and Earth, even when that matter is too faint to see directly. The cosmic microwave background radiation provides a spectacular example of how polarization encodes cosmic history. This radiation is the afterglow of the Big Bang, photons that have been traveling through space for almost 14 billion years since the universe first became transparent. The polarization patterns in this ancient light reveal how matter was distributed in the early universe and how the first structures began to form from tiny quantum fluctuations. Absorption and re-emission signatures provide another type of historical record. When light passes through gas clouds in space, certain wavelengths get absorbed by atoms in the gas, which then re-emit that energy in random directions. This creates dark lines in the spectrum at specific wavelengths, like a fingerprint that identifies which elements the light encountered along its path. These absorption lines tell us about the composition, temperature, density, and motion of the intervening material. If the gas cloud is moving toward or away from us, the absorption lines get shifted to bluer or redder wavelengths due to the Doppler effect. If the gas is hot, the lines become broader. If the gas is dense, some lines become stronger while others become weaker. Each spectrum is like a fossil record of the conditions the light experienced during its journey. To imagine light with perfect memory, we need to understand what such memory might contain and how it could fundamentally change our relationship with the cosmos. Even without memory, light does carry clues about its past. So what counts as a memory in physics? This question takes us into deep philosophical territory about the nature of information, time, and what it means to remember something in a universe governed by quantum mechanics. When we think about memory in everyday life, we usually mean the ability to store information about past events and retrieve it later. Your brain forms memories by creating new connections between neurons, encoding experiences in patterns of electrical and chemical activity that can be recalled days, months, or even decades later. A photograph preserves a memory by capturing light patterns and storing them on film or in digital form. A book records memories by arranging symbols on pages that can be read long after the author wrote them. But what would memory mean for a photon? In the most literal sense, it would require the photon to carry within itself a complete, retrievable record of everything that happened during its journey through space and time. This is radically different from the partial clues that photons carry today. Think about the difference this way. When you look at a photo of a distant galaxy, you are seeing light that left that galaxy millions or billions of years ago. The photons carry information about what the galaxy looked like when the light was emitted, but they do not tell you what happened to the galaxy after the light left, or what the light encountered on its way to your telescope. Now imagine that each photon carried a perfect memory of its entire journey. You could trace its path backwards through space and time, watching everything it experienced along the way. You would see the photon leave a specific star in that distant galaxy, follow its route through interstellar space, observe how it was deflected by gravitational fields, watch it scatter off dust particles, and witness every interaction that shaped its properties during the millions of years of travel. This kind of perfect photonic memory would be like having a time-lapse movie of the universe, recorded from the perspective of every single photon. Each beam of light would be a cosmic historian, carrying an unbroken chain of events from its birth to its arrival at your detector. The implications would be staggering, but before we explore those implications, we need to understand exactly what such a memory would require and why current physics says it should be impossible. The challenge lies in the fundamental nature of information itself and how it behaves in the quantum world. In classical physics, you might imagine that a photon could carry information like a microscopic hard drive, storing data about every interaction in some internal structure. But photons are not classical objects. They are quantum particles with no internal parts, no hidden compartments where information could be stored. According to our best understanding of quantum mechanics, a photon is completely described by its quantum state, which includes properties like energy, momentum, polarization, and phase, but nothing more. The quantum state of a photon contains all the information that physics allows us to know about that particle. If a photon had perfect memory, that information would somehow have to be encoded in its quantum state. But here is where we run into fundamental limits imposed by the laws of physics. First, there is the problem of information capacity. A perfect memory of a photon's journey would require storing an infinite amount of information. Think about all the things that would need to be recorded. The exact trajectory through space, with position coordinates at every moment. The precise timing of every interaction. The details of every scattering event, including the properties of every particle the photon encountered. The gravitational field at every point along the path. The magnetic and electric fields in every region of space the photon traveled through. Even if we limited ourselves to recording interactions only at discrete time intervals, the amount of information would grow without bound as the time intervals became smaller. And quantum mechanics tells us that the universe operates on incredibly small scales, where events happen in time intervals measured in units like Planck time, which is about 10 to the negative 43 seconds. Recording a complete history at this level of detail would require infinite information storage capacity. But the problem goes deeper than just storage capacity. Quantum mechanics imposes fundamental limits on how much information can be extracted from a physical system. The uncertainty principle tells us that we cannot simultaneously know all the properties of a quantum particle with perfect precision. The more accurately we measure one property, the less accurately we can know complementary properties. For photons, this means there are trade-offs between knowing different aspects of their quantum state. If we measure the exact position of a photon, we lose information about its momentum. If we determine its energy precisely, we become uncertain about the timing of when it passed through a particular point. These trade-offs are not due to limitations in our measuring instruments. They reflect fundamental features of how information works in quantum mechanics. There is also the quantum no-cloning theorem, which states that it is impossible to create perfect copies of unknown quantum states. If a photon carried perfect memory, that memory would itself be part of the photon's quantum state. But then, interactions with the environment would necessarily disturb that state, potentially destroying or altering the memory. The no-cloning theorem tells us that we cannot make backup copies of this information to protect it from being lost. Another challenge comes from the process of decoherence. In quantum mechanics, particles can exist in superposition states, where they seem to be in multiple conditions simultaneously, until they are observed or interact with their environment. But interactions with the environment cause decoherence, forcing the quantum system to collapse into one definite state and lose information about the other possibilities. If photons carried quantum memories of their past, those memories would be subject to decoherence whenever the photon interacted with anything in its environment. Each interaction would potentially scramble or erase parts of the historical record, making perfect memory preservation impossible over long journeys through space. Yet despite these fundamental obstacles, it is worth exploring what perfect photonic memory might look like if it could somehow exist. Such a memory would need to encode several types of information about the photon's history. The spatial trajectory would be the most obvious component. This would be a complete record of the photon's path through space, including its position coordinates as a function of time. For a photon that traveled from a distant galaxy, this trajectory would span millions or billions of light years and record every deflection caused by gravitational fields, every change in direction due to scattering, and every curve in the path through warped space-time. The interaction history would catalogue every encounter with matter or energy fields. This would include collisions with individual atoms, passages through magnetic and electric fields, interactions with other photons, and responses to gravitational forces. Each interaction would be recorded with details about the timing, the properties of the other particles or fields involved, and how the interaction changed the photon's quantum state. Timestamps would provide the temporal framework for organizing all this information. But time itself becomes complicated in relativity, where different observers disagree about the timing and simultaneity of events. A perfect photonic memory would need to account for these relativistic effects, possibly by recording proper time as experienced by the photon itself, if such a concept makes sense for a massless particle traveling at the speed of light. Environmental conditions along the path would form another layer of the memory. This would include information about the temperature, density, and composition of the regions through which the photon traveled. For a photon crossing intergalactic space, this might record the properties of the cosmic web, the distribution of dark matter, and the evolution of the expanding universe during the journey. Quantum entanglement relationships would add yet another dimension to the memory. Many photons are created in entangled states with other particles, maintaining mysterious quantum connections that persist even when the particles are separated by vast distances. A perfect memory might need to track these entanglement relationships and how they change over time. The philosophical implications of such complete records are as challenging as the physics. If every photon carried perfect memory, would that memory be accessible to conscious observers? Could we develop technologies to read photonic memories and replay cosmic history? Would this give us a form of time travel, allowing us to witness past events by decoding the memories of ancient light? Even more fundamentally, perfect photonic memory would force us to reconsider the relationship between past, present, and future. If the past were perfectly preserved in traveling photons, it would never truly be gone. Every moment in cosmic history would remain accessible, encoded in the memories of light that witnessed those moments and continues to carry their records through space. This raises questions about the nature of time itself. Does the past exist in some objective sense, or is it just a collection of records and memories? If photons could carry perfect historical records, would that make the past more real? Or would it simply change how we access information about what has already happened? There are also questions about privacy and observation. Perfect photonic memory would mean that every event in the universe, no matter how private or remote, would be recorded by any light present at the scene. The photons from your reading lamp right now would carry records of everything happening in this room. Light from the sun would witness and remember every event on Earth's surface. There would be no truly private moments, because light itself would serve as a universal recording system. But we are getting ahead of ourselves. Before exploring these implications further, we need to examine whether the laws of physics might allow some form of photonic memory to exist, even if it falls short of the perfect record we have been imagining. The answer lies in understanding the subtle ways that information can be encoded in quantum systems, and how those encoding mechanisms might be extended beyond what we observe in nature today. The question is not just whether perfect photonic memory is possible, but whether partial memory, more complete than what we see today, might exist under special circumstances or in exotic physical systems that push the boundaries of our current understanding. This investigation will take us to the frontiers of physics, where theoretical possibilities meet the fundamental limits of what nature allows. Perfect memory implies photons carry infinite information. This statement alone should make us pause, because infinity is not something that appears easily in physics. Every time physicists encounter infinities in their equations, it usually signals that something fundamental is missing from our understanding, or that we are pushing a theory beyond its limits of validity. Yet the idea of infinite information storage is exactly what perfect photonic memory would require. To see why, imagine trying to record the complete history of a single photon traveling from a distant star to Earth. Even if we limited ourselves to recording the photon's position once every second during its journey, we would need to store billions of years' worth of coordinate data. If we wanted higher resolution, recording position every millisecond, the data requirements would multiply by a factor of 1,000. There is no natural stopping point. The more detailed we want the record to be, the more information we need to store. But the challenge goes far deeper than just data storage. Perfect photonic memory would require bypassing some of the most fundamental principles of quantum mechanics, principles that have been tested to extraordinary precision and seem to be built into the very fabric of reality. The first major obstacle is the quantum uncertainty principle, discovered by Werner Heisenberg in 1927. This principle tells us that certain pairs of properties, called complementary variables, cannot be measured simultaneously with perfect precision. For photons, the most important complementary pairs are position and momentum, energy and time, and different components of angular momentum. Here is why this matters for photonic memory. Suppose we want to record a photon's exact trajectory through space. This would require knowing both where the photon is at each moment and how fast it is moving in each direction. But the uncertainty principle forbids us from knowing both position and momentum with perfect precision at the same time. The more accurately we determine the photon's location, the less we can know about its momentum, and vice versa. This is not a technical limitation that we might overcome with better instruments. It represents a fundamental feature of quantum mechanics, reflecting the wave-like nature of matter and energy. A photon is not a tiny ball following a definite path through space. Instead, it is a quantum wave function that spreads out over space and time, with probabilities for being found at different locations, but no single definite trajectory. The uncertainty principle becomes even more problematic when we consider energy and time measurements. To record a perfect timeline of a photon's interactions, we would need to know exactly when each event occurred and exactly how much energy was involved. But quantum mechanics tells us that these two quantities cannot be measured simultaneously with infinite precision. Very brief events can involve uncertain amounts of energy, while precisely defined energy exchanges must occur over extended time periods. Another fundamental barrier comes from the quantum no-cloning theorem, proved by William Wouters and Wojciech Zurek in 1982. This theorem states that it is impossible to create perfect copies of unknown quantum states. The proof is elegant and devastating for any scheme that relies on copying quantum information. Here is how the no-cloning theorem would affect photonic memory. If a photon carried its history as part of its quantum state, then any attempt to read that history would necessarily disturb the photon. In quantum mechanics, measurement is not a passive process like reading words on a page. Instead, measurement involves interaction between the quantum system and a measuring device, and this interaction changes the system being measured. So if we try to extract historical information from a photon's quantum state, we would inevitably alter or destroy some of that information in the process. We could not make a backup copy of the complete historical record to preserve it during the measurement. The no-cloning theorem guarantees that perfect quantum information cannot be duplicated, which means that reading a photon's memory would be a destructive process. The problem of decoherence presents yet another obstacle to perfect photonic memory. Quantum systems can exist in superposition states where they seem to be in multiple conditions simultaneously, but interactions with the environment cause decoherence, forcing the system to collapse into one definite state and lose information about the other possibilities. For a photon traveling through space, decoherence would be almost inevitable. Space is not perfectly empty. It contains sparse gas, dust particles, magnetic fields, gravitational waves, and other photons. Every interaction with these environmental factors would cause partial decoherence of the photon's quantum state, potentially scrambling or erasing parts of its historical memory. The cosmic microwave background radiation presents a particularly interesting case. This ancient light fills all of space, creating a uniform background of photons at a temperature of about 2.7 Kelvin above absolute zero. Any photon traveling through space would constantly interact with this background radiation, leading to decoherence effects that would accumulate over long journeys. But let us set aside these fundamental obstacles for a moment and imagine that perfect photonic memory could somehow exist. What would such a system look like? And how might the information be encoded? The most straightforward approach would be to imagine that each photon carries an internal data structure, like a microscopic library or computer memory. This data structure would contain detailed records of the photon's spatial trajectory, with position coordinates stored as functions of time. For a photon traveling from the Andromeda galaxy, this trajectory would span 2.5 million years and 2.5 million light-years of distance. The trajectory data would need to account for the curved nature of space-time. In Einstein's general relativity, massive objects warp the geometry of space and time, causing light to follow curved paths. A perfect photonic memory would need to record not just the path taken, but also the gravitational fields that shaped that path. This would provide information about the distribution of matter along the route, including dark matter that cannot be observed directly. All interactions with matter and energy fields would need to be catalogued in chronological order. Each entry in this interaction log would specify the timing, location, and nature of the encounter. For collisions with individual atoms, the record would include the type of atom, its energy state before and after the interaction, and how the collision changed the photon's properties. For passages through magnetic fields, the log would document the field strength, orientation, and how the field affected the photon's polarization. Gravitational interactions would form another category in the interaction database. Unlike collisions with matter, gravitational effects are always present and continuously influence a photon's path. The memory would need to record the strength and direction of gravitational fields at every point along the journey, effectively mapping the distribution of mass and energy in the universe as experienced by the traveling photon. Quantum entanglement relationships would add layers of complexity to the memory system. Many photons are created in entangled states with other particles, maintaining mysterious quantum connections that persist even when the particles are separated by vast distances. If one member of an entangled pair is measured or changes state, the other particle instantly responds, regardless of the distance between them. A perfect photonic memory would need to track these entanglement relationships and record how they evolve over time. This might require encoding information about the quantum states of distant particles that the photon has never directly encountered, but remains connected to through the web of quantum correlations that underlies all physical reality. Environmental conditions along the path would provide crucial context for interpreting the interaction data. The memory would need to record the temperature, density, and composition of each region through which the photon traveled. For journeys through intergalactic space, this would include information about the cosmic web, the vast network of filaments and voids that organizes matter on the largest scales. The expansion of the universe itself would need to be recorded as a continuous background effect. As space expands, photons get stretched along with it, causing their wavelengths to increase and their energies to decrease. This cosmological redshift effect accumulates over time, and a perfect memory would need to track exactly how much stretching occurred at each stage of the journey. Timestamps would provide the temporal framework for organizing all this information, but time itself becomes complicated in relativity. Different observers moving at different speeds or located in different gravitational fields will disagree about the timing and simultaneity of events. A photon traveling at the speed of light experiences time dilation, effects that become extreme compared to slower moving particles. From the photon's perspective, if such a perspective makes sense for a massless particle, the journey from a distant galaxy to Earth might take no time at all due to relativistic effects. But from our perspective as observers, the same journey takes millions or billions of years. A perfect photonic memory would need to reconcile these different temporal perspectives and encode timing information in a way that makes sense to all possible observers. The memory system would also need to account for quantum mechanical effects that have no classical analogues. For example, photons can tunnel through barriers that classical physics says should be impenetrable. They can also exhibit interference effects with themselves, behaving as if they travel multiple paths simultaneously, and then recombine to create observable patterns. Recording these quantum effects would require encoding information about probability amplitudes, not just definite outcomes. The memory would need to preserve information about all the possible paths the photon could have taken, weighted by their quantum mechanical probabilities. This would be like recording not just what happened, but also what could have happened and how likely each possibility was. Such a quantum memory system would exist in superposition states, simultaneously encoding multiple possible histories until someone or something measured the photon and collapsed its wave function. This raises deep questions about the relationship between measurement, consciousness, and the storage of information in quantum systems. The theoretical implications of perfect photonic memory extend far beyond just recording cosmic history. Such a system would effectively turn the universe into a vast information processing and storage network, with every photon serving as a mobile hard drive, carrying detailed records of everything it has witnessed. Light would become the universe's ultimate historian, preserving perfect records of every event and making it possible to reconstruct the past with complete accuracy. We could trace the evolution of galaxies, watch the formation of solar systems, and witness the emergence of life on distant worlds by decoding the memories carried by ancient photons. But as we have seen, the laws of physics seem to forbid perfect photonic memory would change everything, not just science, but how we perceive time. Imagine a world where every beam of sunlight streaming through your window carried the complete autobiography of its journey from the sun's core to your eyes, where every glint of starlight held within it the entire history of cosmic evolution, where the simple act of looking up at the night sky would give you access to the universe's most detailed archives. This is not just about having better telescopes or more sensitive detectors. This would fundamentally transform our relationship with the cosmos and our understanding of what it means to observe the universe. We would no longer be passive recipients of whatever information light happens to carry. Instead, we would become cosmic archaeologists, able to excavate the complete history of everything the universe has ever witnessed. Let us start with our own solar system and work our way outward to explore what perfect photonic memory would reveal. Consider the light streaming from our sun right now. In our current understanding, these photons carry information about conditions at the sun's surface, encoded in their wavelengths and intensities. But with perfect memory, each photon would tell a much richer story. We could trace individual photons back to their birthplace in the sun's core, where nuclear fusion converts hydrogen into helium and releases tremendous amounts of energy. The memory would show us exactly which hydrogen nuclei participated in the fusion reaction that created each photon. And we could watch the energy slowly fight its way through the dense layers of the sun's interior. This journey from core to surface takes hundreds of thousands of years in real time, as photons are absorbed and re-emitted countless times by the plasma in the sun's interior. But with perfect photonic memory, we could replay this entire odyssey in detail. We would see how each photon scattered off electrons, got absorbed by atoms in excited states, and emerged from nuclear reactions deep in the stellar furnace. The memory would reveal the sun's internal structure with unprecedented clarity. We could map the temperature, density, and composition at every point inside the star by following the paths of photons as they navigated through different layers. We would watch convection currents carry hot plasma toward the surface and see how magnetic fields twist through the solar interior, occasionally erupting as solar flares and coronal mass ejections. But the story would not end when photons reach the sun's surface. Perfect memory would record their 8-minute journey through space to Earth, documenting every encounter with solar wind particles, cosmic rays, and the tenuous matter of interplanetary space. We could see how the sun's magnetic field extends throughout the solar system and how it interacts with the magnetic fields of planets. When sunlight finally reaches Earth's atmosphere, the photonic memories would reveal the detailed structure of our planet's protective shield. We could watch individual photons scatter off air molecules, creating the blue color of the sky through a process called Rayleigh scattering. We would see how some wavelengths get absorbed by water vapor, ozone, and other atmospheric components, while others pass through to reach the surface. Plant photosynthesis would become visible in extraordinary detail as we watched photons get absorbed by chlorophyll molecules and trigger the chemical reactions that convert carbon dioxide and water into sugar and oxygen. We could follow the energy from individual fusion reactions in the sun's core all the way through to the growth of specific leaves on particular trees. But Earth's story represents just the beginning of what cosmic archaeology with light could reveal. Let us venture beyond our solar system to see what perfect photonic memory might tell us about the formation and evolution of planets around other stars. Consider the light from Proxima Centauri, our nearest stellar neighbor at a distance of 4.2 light-years. With perfect photonic memory, we could decode the complete 4-year journey of each photon as it traveled from that red dwarf star to our telescopes. More importantly, we could see what the star system looked like when the light was emitted, giving us a real-time view of planetary formation and evolution. If Proxima Centauri has planets, and we know it has at least one called Proxima Centauri b, the stellar photons would carry records of every interaction with those worlds. We could watch the planet's atmosphere as it evolved over time, see seasonal changes in its weather patterns, and observe how stellar flares from the volatile red dwarf star affect the planetary environment. For planets in the habitable zone, where liquid water might exist on the surface, photonic memories could reveal the presence of oceans, clouds, and possibly even signs of life. We would not just detect these features as they exist today, but watch their entire evolutionary history unfold as we decoded photons that witnessed different epochs in the planet's development. Rocky planets like Earth leave subtle signatures in the light that reflects off their surfaces and atmospheres. With perfect photonic memory, we could reconstruct the complete geological history of exoplanets by analyzing how their surface compositions changed over time. We could watch continents drift, observe volcanic eruptions, and see how impacts from asteroids and comets shaped planetary surfaces. For gas giant planets, the photonic archives would reveal the complex dynamics of their atmospheric circulation. We could trace the formation of storm systems like Jupiter's Great Red Spot and watch how they evolve over centuries or millennia. We would see how the planets exchange material with their moons and how their magnetic fields interact with charged particles from their host stars. But let us push deeper into space and further back in time to explore what perfect photonic memory could tell us about the formation of entire stellar systems. Consider light from the Orion Nebula, a stellar nursery where new stars are being born just 1,500 light-years from Earth. The photons reaching us today left the nebula 1,500 years ago, carrying records of star formation as it occurred in the medieval period on Earth. With perfect memory, we could decode these photons to watch individual stars condense from the nebula gas and ignite nuclear fusion in their cores. We would see how massive stars blow away the surrounding material with their powerful stellar winds, while smaller stars retain circumstellar disks where planets might eventually form. The entire process of stellar birth, which normally takes millions of years, could be observed in complete detail by analyzing the memories of photons that witness different stages of the process. Protoplanetary disks around young stars would reveal their secrets as we watch dust grains stick together to form larger and larger objects, eventually growing into asteroids, comets, and planets. We could observe how gas giants migrate inward or outward from their original formation sites, and how their gravitational influence shapes the architecture of planetary systems. The formation of double and multiple star systems would become visible as we watched gravitational interactions between protostars in crowded stellar nurseries. We could see how some stars capture companions, while others are ejected from their birth clusters to become solitary wanderers through the galaxy. Extending our archaeological dig even further, let us consider what perfect photonic memory could reveal about the history of entire galaxies. Light from the Andromeda Galaxy, our nearest large galactic neighbor, takes 2.5 million years to reach us. This means we currently see Andromeda as it was when early human ancestors were just beginning to use stone tools on Earth. With perfect photonic memory, we could decode the complete evolutionary history of Andromeda by analyzing photons that left the galaxy at different times over the past several million years. We would watch spiral arms rotate around the galactic center, see how star formation rates change over time, and observe the effects of gravitational interactions with smaller satellite galaxies. The central black hole in Andromeda, which contains the mass of 100 million suns, would reveal its feeding history as we watched material spiral into the accretion disk and disappear beyond the event horizon. We could see how black hole activity affects star formation throughout the galaxy and how jets of high-energy particles stream out from the galactic center. Galactic collisions would become one of the most spectacular shows in our cosmic archaeological collection. The Milky Way and Andromeda are destined to collide in about 4.5 billion years. But with perfect photonic memory, we could study similar collisions that occurred in the past by decoding ancient light from distant galaxy pairs. We would watch as galaxies approach each other over hundreds of millions of years, see how their gravitational fields distort each other's shapes, and observe the burst of star formation triggered when gas clouds from the two galaxies collide and compress. The complex dance of stellar orbits during galactic mergers would be revealed in complete detail, showing how some stars get ejected into intergalactic space, while others spiral toward the merged galaxy's new center. But perhaps the most profound archaeological discoveries would come from the most ancient light in the universe. The cosmic microwave background radiation represents photons that have been traveling for almost 14 billion years, since the universe first became transparent when it was only 380,000 years old. With perfect photonic memory, these ancient photons would carry complete records of the early universe's evolution from the end of the cosmic dark age through the formation of the first stars and galaxies. We could watch the universe's temperature drop as space expanded, see how the first hydrogen and helium atoms formed when electrons combined with nuclei, and observe the tiny density fluctuations that eventually grew into the cosmic web of galaxies and dark matter. The Cosmic Dark Age, a period when the universe contained no stars and emitted no visible light, would no longer be dark to us. Photons from the cosmic microwave background that passed through this era would carry memories of the slow gravitational collapse that led to the first star formation. We could see exactly when and where the first stars ignited, ending the Dark Age and beginning the process of cosmic reionization. Perfect photonic memory would also reveal the nature of dark matter and dark energy by recording their gravitational effects on light throughout cosmic history. We could trace how dark matter halos grew over time and watch how dark energy's repulsive effect gradually accelerated the expansion of the universe. The implications go beyond just understanding cosmic history. Perfect photonic memory would eliminate uncertainty in astronomy and cosmology. Every theory about the universe's evolution could be tested by examining the actual historical records carried by ancient photons. We would know with absolute certainty how galaxies formed when the first stars appeared and what conditions were like in the early universe. Such perfect historical records would also reveal whether we are alone in the universe. Any technological civilization that ever existed would leave traces in the photonic archives. We could see the artificial lights of alien cities, detect the signatures of massive engineering projects, and observe how advanced civilizations modified their planetary environments. But this power would come with profound responsibilities and disturbing implications. If every photon carries perfect memory, then privacy would become impossible on cosmic scales. Any event that occurred in the presence of light would be permanently recorded and potentially accessible to any civilization with the technology to decode photonic memories. The very concept of the past would be transformed. Instead of history being something that happened and then was gone forever, the past would remain present and accessible in the memories of traveling photons. Time would become less like a flowing river and more like a vast library, where every moment is permanently archived and available for retrieval. This transformation of our relationship with time leads us to examine why the universe does not seem to work this way, and what fundamental principles of physics prevent perfect photonic memory from existing in the reality we actually inhabit. But if photonic memory is so powerful, why does nature not already work this way? This question brings us face to face with some of the deepest principles governing our universe, principles that seem almost designed to prevent perfect information storage and make forgetting an inevitable part of physical reality. The answer lies in the quantum mechanical nature of photons and the fundamental limits that quantum mechanics places on information storage and retrieval. These are not technical limitations that we might overcome with better technology, but mathematical theorems that appear to be built into the logical structure of physical reality itself. Let us start with the most basic limitation, the fact that photons do not store past states, only carry current quantum state information. In classical physics, we might imagine that a particle could have internal components or hidden variables that record its history. A classical photon might be like a tiny notebook, accumulating entries about each interaction and carrying that written record forward in time. But quantum mechanics tells us that photons are not classical objects with internal structure. A photon is completely described by its quantum state, which includes properties like energy, momentum, polarization, and phase, but nothing more. There are no hidden compartments where historical information could be stored, no internal memory banks where past interactions could be recorded. The quantum state of a photon contains all the information that physics allows us to extract from that particle. If additional information was somehow encoded in the photon, it would have to be part of the quantum state itself. But quantum states have limited information capacity, and that capacity is already fully utilized by the photon's current properties. More fundamentally, Quantum mechanics operates according to a principle called unitarity, which governs how quantum states evolve over time. Unitary evolution is reversible, meaning that if you know the current state of a quantum system and the laws governing its evolution, you can, in principle, calculate what the state was at any time in the past. But this reversibility comes at a cost. It means that quantum systems cannot accumulate additional information beyond what is needed to specify their current state. Think of it this way. If a photon could store memories of past interactions while still obeying the laws of quantum mechanics, then its quantum state would have to grow more complex over time as new memories were added. But unitary evolution preserves the complexity of quantum states. It cannot increase the amount of information stored in a system without external input. The measurement problem in quantum mechanics creates another fundamental barrier to perfect photonic memory. In quantum mechanics, measurement is not a passive process like reading words on a page. Instead, measurement involves a physical interaction between the quantum system and a measuring device, and this interaction necessarily changes the system being measured. This means that any attempt to read historical information from a photon's quantum state would disturb that state and potentially destroy some of the information we are trying to access. We cannot simply look at a photon's memory without changing the photon itself. The very act of observation alters what we are observing, making perfect information retrieval impossible. The quantum no-cloning theorem, which we discussed earlier, reinforces this limitation. Even if we could somehow read a photon's memory without destroying it, we could not make backup copies of that information to preserve it for future study. The no-cloning theorem guarantees that perfect quantum information cannot be duplicated, which means that accessing photonic memories would necessarily be a destructive process. Decoherence presents perhaps the most serious obstacle to long-term information storage in quantum systems. Quantum systems can exist in superposition states where they seem to be in multiple conditions simultaneously. But interactions with the environment cause decoherence, forcing the system to collapse into one definite state and lose information about the other possibilities. For photons traveling through space, decoherence is almost inevitable. Space is not perfectly empty. It contains sparse gas atoms, dust particles, magnetic fields, gravitational waves, neutrinos, and other photons. Every interaction with these environmental factors causes partial decoherence of the photon's quantum state, gradually scrambling any complex information that might be encoded there. The cosmic microwave background radiation deserves special attention in this context. This ancient light fills all of space with a uniform background of photons at a temperature of about 2.7 Kelvin, above absolute zero. Any photon traveling through space will constantly interact with this background radiation, leading to decoherence effects that accumulate over the millions or billions of years required for intergalactic journeys. Even more subtle effects contribute to decoherence. Virtual particles constantly pop into existence and disappear again due to quantum fluctuations in the vacuum. These virtual particles interact gravitationally with passing photons, causing tiny but cumulative changes to their quantum states. Over long enough time periods and distances, these interactions would scramble any complex information encoded in photonic quantum states. Gravitational interactions provide another source of decoherence. As photons travel through the curved spacetime created by massive objects, their paths are deflected and their frequencies are shifted. These gravitational effects are precisely predictable for the photon's basic properties like energy and momentum, but they would cause chaos for any complex information structures encoded in the quantum state. The expansion of the universe itself contributes to information loss. As space expands, photons are stretched along with it, causing their wavelengths to increase and their energies to decrease. This cosmological redshift effect is smooth and predictable for simple photon properties, but it would gradually degrade any fine-scale information patterns that might be encoded in the quantum state. Thermodynamics provides yet another perspective on why perfect photonic memory seems impossible. The second law of thermodynamics tells us that entropy, a measure of disorder or lost information, always increases in isolated systems. Perfect memory would require decreasing entropy, organizing information in ever more complex patterns without external energy input. But photons traveling through space are not isolated systems. They constantly interact with their environment, exchanging energy and information with other particles and fields. These interactions tend to increase the total entropy of the photon plus environment system, making it impossible to maintain perfectly organized information structures over long periods. The speed of light itself creates temporal paradoxes for photonic memory. From the perspective of a photon traveling at light speed, relativistic time dilation effects become extreme. In the photon's reference frame, if such a reference frame can be defined for a massless particle, the journey from a distant galaxy to Earth takes no time at all. How could a photon record a temporal sequence of events during a journey that, from its own perspective, is instantaneous? Different observers moving at different speeds or located in different gravitational fields will disagree about the timing and order of events that the photon encounters. Special and general relativity tell us that there is no universal time coordinate that all observers agree upon. A perfect photonic memory would need to record events in some objective temporal sequence, but relativity suggests that no such sequence exists. The information paradox in black hole physics provides another example of how quantum mechanics and gravity conspire to prevent perfect information storage. When matter falls into a black hole, the information contained in that matter seems to disappear when the black hole eventually evaporates through Hawking radiation. This apparent violation of quantum mechanical principles has puzzled physicists for decades and suggests that perfect information preservation is incompatible with gravitational effects. Even if we set aside these fundamental obstacles, practical considerations would make perfect photonic memory extraordinarily difficult to implement. The amount of information required to record a complete history would be astronomical. For a photon traveling from the Andromeda galaxy, perfect memory would need to store position coordinates measured billions of times per second for 2.5 million years, along with detailed records of every interaction during that journey. The energy required to encode, store, and maintain such vast amounts of information would likely exceed the energy of the photon itself by many orders of magnitude. Basic considerations from information theory suggest that storing one bit of information requires a minimum energy expenditure, and perfect photonic memory would require storing an essentially infinite number of bits. Quantum error correction presents another challenge. Even if we could somehow encode historical information in photonic quantum states, that information would need to be protected against the inevitable errors introduced by environmental interactions. Quantum error correction is possible in principle, but it requires multiple physical qubits to store each logical bit of information, multiplying the resource requirements by enormous factors. The bandwidth limitations of quantum channels provide yet another constraint. Quantum mechanics places fundamental limits on how much information can be transmitted through any physical system per unit time. These limits, derived from the uncertainty principle and other quantum mechanical constraints, would restrict how much historical information could be encoded in a single photon. All of these limitations point to a deep truth about the nature of physical reality. The universe seems to be designed to forget. Information is constantly being lost to decoherence, dissipated as heat, and scrambled by chaotic interactions. Perfect memory would require fighting against this natural tendency toward forgetting, and the laws of physics seem to make such a fight unwinnable. Yet this tendency toward forgetting is not necessarily a bug in the design of the universe. It might be a feature. The ability to forget and move on may be essential for the universe to continue evolving and creating new complexity. If every interaction were perfectly preserved, the universe might become trapped in an ever-growing archive of its own history, unable to move forward into genuinely new states. The quantum mechanical arrow of time, which distinguishes past from future and gives directionality to physical processes, seems to be intimately connected with the loss of information and the increase of entropy. Perfect memory might be incompatible with the forward flow of time itself, creating paradoxes that could only be resolved by abandoning either memory or temporal progression. But despite all these powerful arguments against perfect photonic memory, there are still some intriguing possibilities at the margins of current physics. Certain exotic quantum states and unusual material environments might allow for enhanced information storage beyond what we normally observe. Some cutting-edge theories even suggest that the universe itself might function as a vast information processing system, with photons playing a crucial role in cosmic computation. These theoretical loopholes do not promise perfect photonic memory, but they hint that light might be capable of carrying more complex information than we currently understand. Exploring these possibilities takes us to the frontiers of physics, where established theories meet speculative ideas about the deepest nature of space, time. Still, there are real effects in physics that feel a little like memory. While perfect photonic memory may be impossible, light does carry partial records of its journey through space and time. These incomplete but precious fragments of cosmic history have revolutionized our understanding of the universe and continue to reveal new secrets about the cosmos we inhabit. The story of light's partial memory begins with one of the most important discoveries in astronomy: the observation that distant objects appear redder than they should. This effect, called cosmological redshift, was first noticed in the early 1900s when astronomers began studying the spectra of distant galaxies and found that familiar patterns of light had been shifted toward longer, redder wavelengths. Redshift functions like a cosmic odometer, automatically recording how far light has traveled through expanding space. As the universe expands, the wavelengths of photons get stretched along with the fabric of space itself. A photon that starts its journey as blue light might arrive at Earth as infrared radiation after traveling for billions of years through the expanding cosmos. The amount of redshift tells us both distance and time. Greater redshift means the light has traveled farther and for longer, showing us objects as they were in the more distant past. The most redshifted galaxies visible to our telescopes have redshift values greater than 10, meaning we see them as they were when the universe was less than 500 million years old, in its cosmic infancy. But redshift is more than just a distance marker. It encodes information about the expansion history of the universe itself. By measuring redshift as a function of distance for thousands of galaxies, astronomers can reconstruct how the expansion rate has changed over cosmic time. This cosmic archaeology revealed one of the most shocking discoveries in modern science: that the expansion of the universe is accelerating, driven by some mysterious dark energy that permeates all of space. The cosmic microwave background provides the most ancient example of light carrying historical information. These photons have been traveling for almost 14 billion years, since the universe was only 380,000 years old and had just become transparent for the first time. Before this epoch of recombination, the universe was so hot and dense that photons could not travel freely. They were constantly absorbed and re-emitted by free electrons in the cosmic plasma. When the temperature finally dropped low enough for electrons and protons to combine into neutral hydrogen atoms, photons were suddenly liberated to travel freely through space. The cosmic microwave background is the afterglow of this moment, the last light emitted before the universe entered its cosmic dark age and began the slow process of forming the first stars. These ancient photons carry within their properties a detailed record of conditions in the early universe. tiny temperature variations in the cosmic microwave background, measured to be only a few parts in 100,000, represent the seeds from which all cosmic structure eventually grew. These fluctuations show us the distribution of matter and energy when the universe was young and relatively smooth, before gravity had time to amplify small differences into the vast web of galaxies and empty space we see today. The polarization of cosmic microwave background photons provides even deeper archaeological information. When light scatters off free electrons, it becomes polarized in characteristic patterns that depend on the distribution and motion of the scattering material. By mapping the polarization across the sky, astronomers can reconstruct the velocities of matter in the early universe and see how the first large-scale structures began to form. Recent measurements of cosmic microwave background polarization have even detected gravitational waves from the first fraction of a second after the Big Bang, when the universe underwent a period of exponential expansion called cosmic inflation. These primordial gravitational waves left their signature in the polarization patterns of the ancient light, providing a window into physics at energy scales far beyond anything we can recreate in terrestrial laboratories. Starlight carries its own forms of partial memory, encoded in the spectral lines that reveal the composition, temperature, and motion of stellar atmospheres. When light passes through the outer layers of a star, atoms in the stellar atmosphere absorb specific wavelengths characteristic of their electronic structure. This creates dark absorption lines in the stellar spectrum, like a barcode that identifies which elements are present in the star. But these spectral lines carry more information than just chemical composition. The strength and width of the lines reveal the temperature and pressure in the stellar atmosphere. Magnetic fields in the star split some spectral lines into multiple components through the Zeeman effect, allowing astronomers to map stellar magnetic fields with exquisite precision. The exact wavelengths of the lines are shifted by the Doppler effect if the star is moving toward or away from us, revealing stellar velocities and the orbital motions of binary star systems. Some of the most dramatic examples of light's partial memory come from observations of supernovae, the explosive deaths of massive stars. When a star explodes as a supernova, it briefly outshines an entire galaxy and ejects material at speeds of thousands of kilometers per second. The light from these explosions carries detailed records of the nuclear processes that occur during stellar death. Type Ia supernovae, which result from the explosion of white dwarf stars, provide particularly valuable historical information. These explosions are remarkably uniform in their properties, making them excellent standard candles for measuring cosmic distances. By observing type Ia supernovae at different redshifts, astronomers can trace the expansion history of the universe and study how dark energy has affected cosmic evolution over billions of years. The light curves of supernovae, which show how their brightness changes over time, encode information about the explosion mechanism and the properties of the progenitor star. Different types of supernovae show characteristic patterns in their light curves, allowing astronomers to classify stellar explosions and understand the various ways that stars can die. Supernova spectra reveal the elements created during stellar nucleosynthesis and explosive burning. Heavy elements like iron, nickel, and cobalt are forged in the intense heat and pressure of stellar cores and supernova explosions. The spectral lines from these elements tell us about the nuclear physics of stellar death and how the universe gradually enriched itself with the building blocks of planets and life. Gravitational lensing provides another fascinating example of how light encodes historical information. When light passes near massive objects like galaxies or black holes, the curvature of space-time bends the photon paths and can magnify, distort, or create multiple images of background objects. The amount and pattern of lensing distortion depends on the mass distribution of the lensing object and the geometry of the light path. Strong gravitational lensing can create spectacular Einstein rings, where the image of a background galaxy is stretched into a perfect circle around the lensing mass. Multiple images of the same background object can appear at different positions on the sky, each following a slightly different path around the gravitational lens. If the background object varies in brightness, these multiple images will show the same variability pattern but at different times, with time delays that depend on the path differences. Weak gravitational lensing causes more subtle distortions that can only be detected statistically by studying the shapes of many background galaxies. This weak lensing effect allows astronomers to map the distribution of dark matter in the universe, since dark matter contributes to gravitational lensing, even though it cannot be seen directly. The cosmic shear patterns created by weak lensing provide a direct probe of how cosmic structure has grown over time. Microlensing occurs when compact objects like stars or planets pass in front of more distant light sources, causing temporary brightening due to gravitational focusing. This effect has been used to discover exoplanets and study the population of dark, compact objects in our galaxy. The light curves of microlensing events encode information about the masses and orbital properties of the lensing objects. Interstellar dust provides another mechanism for encoding information in starlight. As photons travel through the galaxy, they encounter tiny, solid particles floating in interstellar space. These dust grains absorb and scatter light in wavelength-dependent ways, preferentially affecting blue light more than red light, and causing distant stars to appear redder and dimmer than they would in empty space. But interstellar extinction is not just an obstacle to clear observations, it also carries information about the intervening material. The wavelength dependence of extinction reveals the size distribution and composition of dust grains. Polarization measurements show how dust grains are aligned by magnetic fields in interstellar space, providing a way to map the galactic magnetic field structure. Different types of interstellar environments leave characteristic signatures in starlight. Dense molecular clouds, where new stars are forming, contain complex organic molecules that create distinctive absorption features. Supernova remnants and stellar wind bubbles have their own spectral signatures that reveal how massive stars affect their surroundings during their lives and deaths. The phenomenon of interstellar scintillation, similar to the twinkling of stars caused by Earth's atmosphere, provides information about turbulence in the interstellar medium. Radio waves from distant pulsars twinkle as they pass through irregularities in the ionized gas between stars. The pattern and timescale of this scintillation reveals the structure and dynamics of interstellar plasma on scales too small to observe directly. Pulsar timing offers one of the most precise examples of how light encodes astronomical information. Pulsars are rapidly rotating neutron stars that emit beams of radiation like cosmic lighthouses. The arrival times of pulsar pulses can be measured with extraordinary precision, revealing tiny changes in the pulsar's rotation period and orbit if it is part of a binary system. These timing measurements have led to remarkable discoveries, including the first indirect detection of gravitational waves through their effect on the orbital decay of a binary pulsar system. Pulsar timing arrays, which monitor many pulsars simultaneously, are now being used to search for gravitational waves from supermassive black hole mergers throughout the universe. Even the simple fact that we can see stars and galaxies encodes historical information about cosmic transparency. The universe has not always been transparent to light. During the cosmic dark ages, before the first stars formed, the universe was filled with neutral hydrogen that absorbed most photons. The reionization of this hydrogen by the first generation of stars and quasars gradually made the universe transparent again. And we can study this process by looking at how the transparency changes with cosmic distance and time. The Lyman Alpha Forest provides a particularly beautiful example of this cosmic archaeology. Light from distant quasars shows a forest of absorption lines created by neutral hydrogen clouds at various redshifts along the line of sight. The pattern and strength of these absorption lines reveals the distribution and evolution of intergalactic gas over cosmic time, showing how the universe gradually became Ryanized and how large-scale structure grew from initial density fluctuations. All of these effects represent fragments of cosmic memory preserved in light. While far from the perfect historical records we imagined earlier, these partial memories have enabled unprecedented discoveries about the universe and our place within it. They show us that even without perfect memory, light serves as a remarkably detailed cosmic messenger, carrying information about phenomena and processes across vast scales of space and time. The question remains whether light might be capable of carrying even more information than we currently understand how to extract. Some frontier theories suggest that quantum mechanics and space-time itself might have hidden layers of complexity that could support enhanced information storage and transmission beyond what classical physics would allow. Some frontier theories even suggest light might carry deeper records if space itself works differently than we think. While the fundamental laws of quantum mechanics seem to forbid perfect photonic memory, physicists have discovered some intriguing theoretical possibilities that might allow enhanced information storage beyond what we normally observe in nature. These are not proven phenomena, but rather speculative ideas emerging from the cutting edge of theoretical physics, where our understanding of quantum mechanics, space-time, and information theory is being pushed to its absolute limits. Some of these concepts might represent genuine loopholes in our current understanding, while others might turn out to be impossible for reasons we do not yet comprehend. The search for these theoretical possibilities takes us into the most exotic corners of modern physics, where reality becomes stranger than science fiction, and where the boundaries between the possible and impossible blur in unexpected ways. Here, at the frontiers of human knowledge, we encounter ideas so radical that they challenge our most basic assumptions about the nature of space, time, and information itself. Let us begin with quantum entanglement, one of the most mysterious and counterintuitive phenomena in quantum mechanics. When two particles become entangled, they share a quantum connection that persists even when the particles are separated by vast distances. Measuring one particle instantly affects the state of its entangled partner, regardless of how far apart they are. Einstein famously called this effect spooky action at a distance and spent years trying to prove that quantum entanglement could not really exist. But decades of experiments have confirmed that entanglement is indeed real and represents a fundamental feature of quantum reality. Entangled particles remain connected through what physicists call non-local correlations, maintaining shared quantum information even across cosmic distances. The phenomenon becomes even more remarkable when we consider that entanglement can involve not just two particles, but entire networks of quantum systems. Scientists have created entangled states involving dozens of photons, atoms, and even macroscopic objects like superconducting circuits. These quantum networks can maintain their correlations for surprisingly long periods, suggesting that entanglement might be more robust than previously thought. Now imagine that photons could become entangled not just with other particles, but with the entire environment through which they travel. Instead of losing information to decoherence, a photon might become quantum mechanically entangled with every atom, field, and particle it encounters along its journey. This entanglement network could serve as a distributed storage system, preserving historical information across multiple physical systems rather than trying to encode everything within the photon itself. In this scenario, the photon would not carry complete memories internally, but it would maintain quantum correlations with all the systems that witnessed its passage. By measuring these correlations, it might be possible to reconstruct the photon's history from the entangled environmental records. The universe itself would become a vast quantum computer, with entanglement serving as the mechanism for preserving and accessing historical information. The scale of such an entanglement network would be truly cosmic. A single photon traveling from the Andromeda Galaxy would potentially become entangled with trillions upon trillions of particles during its 2.5 million year journey to Earth. Each gas atom in interstellar space, each dust grain in molecular clouds, and each electron in the cosmic plasma could become part of the photon's distributed memory system. This idea pushes against the boundaries of what we understand about decoherence and the measurement problem in quantum mechanics. Normally, entanglement with the environment destroys quantum coherence and scrambles information. But some theories suggest that under special circumstances, environmental entanglement might actually preserve information in new and unexpected ways. Recent research in quantum information theory has revealed that decoherence is not always destructive. In some cases, environmental interactions can actually protect quantum information through a process called decoherence-free subspaces. These are special quantum states that remain unaffected by certain types of environmental noise, potentially allowing information to survive even in chaotic environments. The holographic principle provides another intriguing possibility for enhanced photonic memory. This principle, which emerged from studies of black hole physics, suggests that all the information contained within any volume of space can be encoded on the boundary surface of that volume. In other words, three-dimensional reality might be a projection from information stored on a two-dimensional surface, like a hologram. The holographic principle was first proposed to solve the black hole information paradox, which asks what happens to information when matter falls into a black hole. Stephen Hawking's discovery that black holes evaporate through quantum radiation seemed to imply that information could be destroyed, violating a fundamental principle of quantum mechanics. The holographic principle suggests that this information is not destroyed, but rather encoded on the black hole's event horizon surface. If the holographic principle is correct, then photons traveling through space might have access to information encoded on distant boundary surfaces. A photon passing through our galaxy could potentially read information about the entire galactic volume from data encoded on the galaxy's edge. This would not be memory in the conventional sense, but rather a form of non-local information access that transcends normal limitations of space and time. The mathematics of holography reveals that this boundary encoding is remarkably efficient. The surface area of a sphere, measured in units of the Planck length squared, equals the maximum amount of information that can be contained within that sphere. This means that the two-dimensional boundary contains exactly enough storage capacity to encode everything happening in the three-dimensional interior. The holographic principle is most well developed in the context of black holes, where it suggests that information falling into a black hole is not destroyed, but rather encoded on the black hole's event horizon surface. Some physicists speculate that similar holographic encoding might occur throughout the universe, with information about cosmic events preserved on various boundary surfaces that photons could potentially access. One of the most remarkable realizations of holographic ideas is the ADS-CFT correspondence, discovered by Juan Maldacena in 1997. This mathematical framework shows that certain theories of quantum gravity in curved spacetime are equivalent to quantum field theories living on the boundary of that spacetime. While these are highly abstract mathematical constructions, they demonstrate that holographic encoding of information is not just speculation, but a well-established feature of theoretical physics. String theory, our most ambitious attempt to unify all the forces of physics, suggests that space itself might have a complex internal structure at the smallest scales. According to string theory, what we think of as empty space is actually filled with tiny vibrating strings and higher dimensional objects called branes. These fundamental structures might provide additional mechanisms for information storage and transmission. The strings in string theory are unimaginably small, with lengths on the order of the Planck length, about 10 to the negative 35 meters. At these scales, the familiar concepts of space and time break down, and reality becomes a quantum foam of fluctuating geometry. Yet even in this chaotic environment, the vibrating strings maintain coherent patterns that could potentially encode information. In some string theory models, photons are not elementary particles, but rather collective vibrations of the underlying string network. If this picture is correct, then photons might have access to information encoded in the structure of space itself. The strings that make up space-time could serve as a cosmic memory bank, preserving records of events and allowing photons to read this information as they propagate through the string network. The mathematics of string theory requires additional spatial dimensions beyond the 3 we observe in everyday life. Most string theories need 9 or 10 spatial dimensions to be mathematically consistent. These extra dimensions are thought to be compactified, meaning they are curled up so small that we cannot detect them directly with current technology. Extra dimensions, if they exist, could provide additional storage space for photonic memories. String theory predicts that space has more than the 3 dimensions we observe, with the extra dimensions curled up so small that we cannot detect them directly. But quantum effects might allow information to leak into these hidden dimensions, where it could be preserved and potentially retrieved by properly designed measurements. The geometry of these compactified dimensions is incredibly complex, involving mathematical objects called Calabi-Yau manifolds that can have hundreds or even thousands of topological features. Each of these features could potentially serve as a storage location for information, creating a vast hidden archive that exists parallel to our familiar 3-dimensional space. Some theories suggest that photons might oscillate between our familiar 3-dimensional space and these extra dimensions during their journey. Information encoded in the extra-dimensional components of the photon's wave function could survive interactions that would destroy memories stored in ordinary 3-dimensional space. This would be like having a secret compartment where historical records could be hidden from the decoherence effects that plague normal information storage. The physics of extra dimensions becomes even more exotic when we consider the possibility of large extra dimensions, proposed by physicists like Nima Arkani-Hamed and Savas Dimopoulos. In these theories, gravity might propagate through large extra dimensions while other forces remain confined to our 3-dimensional space. This could create gravitational memory effects that preserve information about mass distributions in ways that are invisible to electromagnetic observations. Metamaterials and engineered quantum systems provide more concrete possibilities for enhanced photonic information storage. These are artificial materials designed to have electromagnetic properties not found in nature, created by arranging ordinary matter in carefully controlled patterns at scales smaller than the wavelength of light. The field of metamaterials has exploded in recent decades, with researchers creating materials that have negative refractive indices, perfect absorption at specific wavelengths, and even cloaking properties that can make objects invisible. These exotic electromagnetic properties arise from the careful engineering of the material's structure at the nanoscale, creating effective properties that can be radically different from those of the constituent materials. Some metamaterials can slow light down to walking speeds or even bring it to a complete stop, trapping photons in quantum superposition states for extended periods. Other metamaterials can create negative refractive indices, causing light to bend backwards in ways that violate our everyday intuitions about optics. These exotic properties might provide new mechanisms for encoding and preserving information in photonic systems. Slow light phenomena are particularly intriguing for information storage applications. When light propagates through certain atomic gases cooled to near absolute zero, its group velocity can be reduced to just a few meters per second. In extreme cases, light pulses can be brought to a complete stop, and stored in the atomic medium for minutes or even hours before being released to continue their journey. Quantum memories based on trapped atoms or ions can already store photonic quantum states for seconds or minutes before decoherence destroys the information. Future advances in quantum error correction and quantum control might extend these storage times indefinitely, creating practical systems for long-term photonic memory storage. The most advanced quantum memory systems use clouds of ultra-cold atoms trapped in optical lattices, where individual atoms can be controlled with extraordinary precision. These systems can store not just the energy and polarization of photons, but also their complete quantum states, including subtle phase relationships and entanglement properties. Slow light phenomena in special materials could also enhance information storage capacity. When light propagates through certain atomic gases or photonic crystals, its speed can be reduced by factors of millions or billions compared to the speed of light in vacuum. This dramatic slowdown might allow more complex information patterns to be encoded in the photon's quantum state without violating fundamental limits on information density. Photonic crystals represent another promising approach to enhanced light-matter interactions. These are materials with periodic variations in their refractive index that create photonic band gaps, regions of wavelength where light cannot propagate. By carefully designing the crystal structure, researchers can create cavities that trap light for extended periods, or waveguides that control light propagation with extraordinary precision. The concept of quantum error correction offers another potential pathway to enhanced photonic memory. Just as classical computers use error-correcting codes to protect information from noise and corruption, quantum systems can use quantum error correction to preserve fragile quantum information against decoherence. Quantum error correction works by encoding each logical qubit of information across multiple physical qubits in a carefully designed pattern. When errors occur, they can be detected and corrected without destroying the encoded information. The most promising quantum error correcting codes can tolerate error rates of up to 1%, making them practical for real-world quantum computing applications. In principle, quantum error correction could allow arbitrarily long preservation of quantum information, provided that the error correction process operates faster than the rate of decoherence. For photonic systems, this would require distributing the information across multiple photons and constantly performing quantum error correction operations to maintain coherence. The technical challenges of implementing quantum error correction for traveling photons are formidable. The correction operations would need to be performed continuously as the photons propagate through space, requiring a network of quantum processing stations that could detect and correct errors without destroying the encoded information. Some theoretical proposals suggest that the universe itself might naturally implement quantum error correction on cosmic scales. If space-time has a discrete structure at the Planck scale, as suggested by some approaches to quantum gravity, then the universe might automatically protect certain types of information against loss or corruption. Loop quantum gravity, an alternative approach to unifying quantum mechanics and general relativity, suggests that space and time are not continuous, but rather made up of discrete units at the smallest scales. In this picture, space-time itself has a granular structure, like pixels on a cosmic computer screen. Information might be naturally preserved in this discrete structure, protected against continuous decoherence processes by the fundamental discreteness of space and time. The mathematical framework of loop quantum gravity replaces the smooth geometry of Einstein's general relativity with a discrete network of quantum geometric degrees of freedom. Space becomes a quantum superposition of different geometric configurations, with area and volume taking on discrete values, measured in units of the Planck length and Planck volume. Causal dynamical triangulation and other approaches to quantum gravity also suggest that space-time might have an underlying computational structure. If the universe is fundamentally a quantum computer, as some physicists speculate, then photons might serve as information carriers in cosmic-scale computation processes. The memories we seek might be encoded not in individual photons, but in the computational patterns that emerge from large-scale quantum processing. These digital approaches to quantum gravity attempt to construct space-time from fundamental discrete building blocks, similar to how computer simulations construct virtual worlds from pixels and voxels. In causal dynamical triangulation, space-time is built from four-dimensional simplices, the four-dimensional analogues of triangles, assembled according to rules that preserve causality. The many worlds interpretation of quantum mechanics provides perhaps the most radical possibility for photonic memory. According to this interpretation, every quantum measurement causes the universe to split into multiple parallel branches, each corresponding to a different measurement outcome. If this interpretation is correct, then perfect information about quantum systems is preserved across the ensemble of parallel universes, even though individual observers can only access limited information within their particular branch. The many worlds interpretation was first proposed by Hugh Everett III in 1957 as a way to solve the measurement problem in quantum mechanics. Instead of quantum wave functions collapsing when measurements are made, Everett suggested that all possible outcomes actually occur, but in different parallel branches of reality. In the many worlds picture, photons might carry memories that span multiple parallel universes. While we cannot access information from other branches directly, quantum interference effects between different branches might leave subtle signatures that preserve historical information. Reading these memories would require measuring quantum interference patterns across multiple parallel copies of the same photon, a process that seems impossible with current technology, but might be achievable with advanced quantum measurement techniques. The implications of many worlds' photonic memory are staggering. Every photon would carry not just information about the single history that occurred in our branch of reality, but about all the possible histories that occurred across the entire multiverse. This would be like having access to a cosmic library containing every possible version of events, with each book representing a different branch of the quantum multiverse. Conscious observation itself might play a role in photonic memory, according to some interpretations of quantum mechanics. If consciousness is necessary to collapse quantum wave functions and determine the outcomes of measurements, then conscious observers might leave traces in the quantum states of photons they observe. These consciousness-induced modifications could serve as a form of photonic memory, preserving records of which events were witnessed by conscious beings. This idea pushes into highly speculative territory where physics meets philosophy and cognitive science. We do not yet understand the relationship between consciousness and quantum mechanics, or even whether such a relationship exists. But if consciousness does play a fundamental role in quantum measurement, then the universe might naturally preserve records of conscious observation events in the quantum states of light. The hard problem of consciousness, which asks how subjective experience arises from objective physical processes, remains one of the deepest mysteries in science. Some physicists and philosophers have proposed that consciousness might be a fundamental feature of reality, like mass or charge, rather than an emergent property of complex information processing. Time travel paradoxes provide another avenue for exploring enhanced photonic memory. If closed time-like curves exist in our universe, as allowed by some solutions to Einstein's field equations, then photons might be able to travel backwards in time and interact with their own past states. This could create causal loops where photons preserve information about future events and carry those records backwards in time. Einstein's equations of general relativity allow for exotic space-time geometries that contain closed time-like curves, paths through space-time that loop back to their own past. These include solutions like the Gödel universe, traversable wormholes, and space-times containing cosmic strings or rotating black holes. While most physicists believe that nature prevents paradox, creating time travel through mechanisms we do not yet understand, the theoretical possibility remains open. Photons traveling through exotic space-time geometries near rotating black holes or cosmic strings might experience closed time-like curves and develop memory capabilities that transcend normal limitations of causality. The grandfather paradox and other temporal paradoxes suggest that time travel might be self-consistently constrained by the requirement that the past cannot be changed. In this view, any information that photons carry backwards in time would already be part of the historical record, creating a self-consistent causal loop with no beginning or end. Quantum tunneling provides yet another potential mechanism for enhanced photonic memory. Under normal circumstances, photons cannot penetrate barriers that classical physics says should be impenetrable. But quantum mechanics allows particles to tunnel through barriers with small but non-zero probability. If information could be encoded in the tunneling process itself, photons might be able to access historical records stored in otherwise inaccessible regions of space. Quantum tunneling is one of the most counterintuitive phenomena in quantum mechanics, allowing particles to pass through energy barriers that should be impossible to cross according to classical physics. The probability of tunneling depends exponentially on the barrier height and width, making it extremely rare for macroscopic objects but relatively common for quantum particles. Photonic tunneling occurs when light encounters interfaces between materials with different refractive indices. Even when total internal reflection should prevent light from crossing the interface, a small fraction of the photons can tunnel through and continue propagating in the second medium. This effect is used in devices like tunnel junction photodetectors and quantum dot light emitting diodes. These theoretical possibilities represent the current frontiers of our understanding about information, quantum mechanics, and the nature of space and time. While none of them guarantee that enhanced photonic memory is possible, they suggest that our current understanding of fundamental limits might be incomplete. The universe may have deeper layers of complexity that could support information storage and retrieval mechanisms beyond what we currently imagine. The mathematical frameworks underlying these theories are often so abstract and complex that their physical implications remain unclear even to the researchers developing them. String theory, for example, involves calculations in 10 or 11-dimensional spacetimes using mathematical tools that push the boundaries of human understanding. But even if some form of enhanced photonic memory turns out to be possible, it would likely fall far short of the perfect historical records we explored earlier. The fundamental tension between information preservation and the forward flow of time seems to be built into the logical structure of physical reality itself. Perfect memory might be incompatible with the universe's ability to evolve and create genuinely new patterns of matter and energy. The second law of thermodynamics, which requires entropy to increase over time, provides a fundamental arrow of time that distinguishes past from future. Perfect information preservation would require decreasing entropy, organizing information in ever more complex patterns without external energy input. This appears to be fundamentally incompatible with the thermodynamic evolution of the universe. The implications of even limited enhanced photonic memory would be profound, not just for science, but for philosophy, consciousness, and our understanding of what it means to exist in a universe where the past might be more accessible than we ever imagined. These theoretical explorations push us to reconsider our most basic assumptions about reality and to remain open to possibilities that currently seem impossible, but might someday transform our understanding of the cosmos. If light could remember perfectly, the implications would go beyond science and transform every aspect of human existence. The social, philosophical, and ethical consequences of perfect photonic memory would be so profound that they might fundamentally alter what it means to be human and how we relate to each other, to privacy, to truth, and to the nature of time itself. privacy would be the first casualty of perfect photonic memory. In our current world, privacy depends on the fact that most events are witnessed by only a limited number of people, and that human memory is fallible and selective. We can have private conversations, intimate moments, and personal experiences that remain known only to those directly involved. But if every photon carried perfect memory, then any light present during an event would preserve a complete, retrievable record of everything that happened. The photons bouncing off your face right now as you read these words would carry detailed information about your exact location, your facial expressions, your surroundings, and potentially even your emotional state, as revealed through micro-expressions and physiological responses. The sunlight streaming through your window would be recording everything happening in your room with perfect fidelity. The artificial lights in your home would be accumulating comprehensive archives of your daily activities, your interactions with family members, your private conversations, and your most personal moments. There would be no such thing as a truly private space, because light itself would serve as an omnipresent witness and recorder. This surveillance would not be limited to government agencies or corporations with advanced technology. Anyone with the ability to intercept and decode photonic memories would have access to these records. The light from your reading lamp could theoretically be captured and analyzed by anyone with a view into your window, your neighbor across the street, or even astronomers on distant planets if they had sufficiently advanced technology. The implications extend far beyond individual privacy to encompass entire societies and civilizations. Every city would be constantly bathed in light, carrying complete records of all human activities. Street lights, car headlights, neon signs, and building illumination would create an inescapable network of surveillance that makes our current concerns about digital privacy seem quaint by comparison. Historical truth would undergo a fundamental transformation. In our current world, historical records are incomplete, biased, and often contradictory. We rely on documents, artifacts, and human testimony to reconstruct past events, knowing that these sources are always partial and potentially unreliable. Historians spend their careers trying to piece together accurate pictures of what really happened in the past. With perfect photonic memory, historical uncertainty would largely disappear. Any event that occurred in the presence of light would be perfectly preserved and completely verifiable. We could settle historical debates definitively by consulting the memories of photons that witnessed the events in question. Did Julius Caesar really say "et tu Brute" when he was assassinated? We could know for certain by decoding the memories of sunlight that illuminated the Roman Senate on the Ides of March. But this historical clarity would come at the cost of mystery, interpretation, and the creative human process of trying to understand the past. Much of what makes history interesting is precisely its incompleteness and ambiguity. The gaps in our knowledge allow for different interpretations, scholarly debate, and the gradual evolution of our understanding as new evidence emerges. Perfect historical records might also be psychologically overwhelming. Humans have evolved to forget most of the details of our daily experiences, retaining only the most significant memories and allowing the rest to fade. This forgetting is not a bug, but a feature of human psychology, protecting us from being overwhelmed by irrelevant information and allowing us to focus on what matters most. If every moment of human history were perfectly preserved and accessible, we might find ourselves drowning in an ocean of information about the past. The sheer volume of available historical data could paralyze decision-making and prevent us from moving forward into the future. We might become a species obsessed with reliving and reanalyzing past events rather than creating new experiences. The concept of personal growth and redemption would face serious challenges in a world with perfect photonic memory. Currently, people can learn from their mistakes, change their behavior, and move on from past errors in judgment. Society generally allows for second chances and the possibility that individuals can evolve and improve over time. But perfect memory would preserve every embarrassing moment, every poor decision, and every moral failing for all time. The stupid things you said as a teenager, the mistakes you made in your 20s, and the regrettable actions of your youth would be permanently encoded in light and potentially accessible to anyone with the technology to read photonic memories. This permanence could create a society where past mistakes define people forever, where growth and change become impossible because everyone's worst moments are preserved in perfect detail. The psychological burden of knowing that every action is being permanently recorded might lead to extreme self-consciousness and social paralysis. Legal systems would face unprecedented challenges and opportunities. On one hand, perfect photonic memory would provide unimpeachable evidence for legal proceedings. Crime scenes would be perfectly preserved in the memories of light present during the events. Witness testimony would become unnecessary because we could simply replay the actual events from the perspective of photons that were there. This could lead to a dramatic improvement in justice, with innocent people being exonerated and guilty parties being convicted based on irrefutable evidence. Cold cases could be solved by analyzing the memories of ancient photons, potentially bringing closure to victims' families and ensuring that justice is served regardless of how much time has passed. But the legal implications extend far beyond criminal justice. Contract disputes could be settled by examining the memories of photons present during negotiations. Divorce proceedings could involve reviewing the complete history of a marriage as recorded by household lighting. Personal injury cases could be resolved by analyzing the exact sequence of events leading to accidents. The availability of such comprehensive evidence might actually complicate rather than simplify legal proceedings. Lawyers would need to become experts in photonic memory analysis, and courts would need to develop new standards for evaluating and interpreting this evidence. The sheer volume of available information could make trials extremely lengthy and complex. Religious and spiritual beliefs would face profound challenges from perfect photonic memory. Many religious traditions rely on faith, mystery, and the inability to definitively prove or disprove spiritual claims. Sacred texts often describe miraculous events that occurred in the distant past, events that believers accept on faith despite the lack of contemporary evidence. If perfect photonic memory existed, we could potentially verify or refute many religious claims by consulting the memories of light present during alleged miraculous events. Did Moses really part the Red Sea? Did Jesus actually walk on water? Did Muhammad really ascend to heaven from Jerusalem? The photonic archives might provide definitive answers to these questions. For some believers, such verification might strengthen their faith by providing proof of divine intervention. But for others, the absence of miraculous events in the photonic record might challenge fundamental beliefs and create spiritual crises. The role of faith itself might change if spiritual claims could be subjected to objective verification. Even more fundamentally, perfect photonic memory might reveal that consciousness and free will are illusions. If every human action could be traced back through a complete causal chain recorded in perfect detail, we might discover that all behavior is strictly determined by prior events. The sense of making free choices might turn out to be a psychological construct with no basis in physical reality. Educational systems would be revolutionized by access to perfect historical records. Students could witness any event in human history firsthand by decoding the appropriate photonic memories. Instead of reading about the American Revolution, students could watch the actual battles unfold. Rather than studying the construction of the pyramids from textbooks, they could observe the ancient Egyptians at work. This immersive historical education could create a much deeper understanding of past events and their context. Students would no longer need to rely on potentially biased accounts written by historians with particular perspectives. They could form their own opinions based on direct observation of historical events. But perfect historical access might also eliminate the skills of historical analysis, critical thinking, and dealing with uncertainty that are currently essential parts of education. If everything is perfectly preserved and accessible, students might never learn to evaluate conflicting sources, weigh evidence, or make judgments based on incomplete information. The relationship between individual identity and memory would become incredibly complex. Currently, we think of personal identity as being closely tied to our memories of past experiences. We are who we are, partly because of what we remember about our lives, our relationships, and our personal histories. If perfect photonic memories preserved every moment of everyone's life in complete detail, the boundaries between individual and collective memory might blur. Your personal history would not belong only to you, but would be accessible to anyone who could decode the photonic records of your life. The privacy of memory, which is currently absolute, would disappear entirely. This might lead to a more collective form of consciousness, where individual experiences become part of a shared repository of human memory. People might begin to think of themselves not as isolated individuals, but as temporary patterns in a vast network of interconnected experiences preserved in light. Interpersonal relationships would be fundamentally altered by the elimination of privacy and the availability of perfect memory. Trust, which currently depends partly on the impossibility of knowing everything about another person, might become irrelevant when complete information is available. The gradual process of getting to know someone, with its elements of mystery and discovery, could be replaced by instant access to their complete life history. Intimacy might require redefinition when privacy no longer exists. Currently, intimate relationships involve sharing personal information and experiences that are not available to the general public. But if all information is equally accessible to everyone, intimacy might need to be based on emotional connection, rather than exclusive access to personal knowledge. The concept of forgiveness might also change when perfect memory makes it impossible to forget. Currently, forgiving someone often involves a conscious decision to stop dwelling on their past actions and to move forward in the relationship. But perfect photonic memory would make those past actions permanently accessible and impossible to truly forget. Perhaps most profoundly, perfect photonic memory would alter our relationship with time itself. Currently, the past feels fundamentally different from the present because it is inaccessible except through imperfect records and fading memories. The past is gone, existing only in traces and reconstructions. But if the past were perfectly preserved in traveling photons, it would remain present and accessible indefinitely. Time might feel less like a flowing river and more like a vast library where every moment is permanently archived and available for retrieval. The psychological experience of temporal flow could be replaced by a sense of all moments existing simultaneously in the cosmic archive of light. This transformation of our relationship with time could have profound implications for how we live our lives. If every moment is permanently preserved, each action and decision might feel weighted with eternal significance. The fleeting nature of experience, which currently gives life much of its poignancy and meaning, would be replaced by the knowledge that nothing ever truly passes away. Whether such a transformation would enhance or diminish human experience remains an open question that pushes us to consider what we truly value about privacy, forgetting, and the passage of time in our current existence. Photons may not carry a perfect diary of their lives, but they do carry enough for us to piece together a remarkable cosmic story. From the cosmic microwave background's frozen whispers to the red glow of ancient galaxies, light is already our time machine. Perfect memory might never exist, but in the photons we catch, the universe has already left us its autobiography. As we reach the end of our exploration into photonic memory, it is worth reflecting on the extraordinary journey we have taken through the realms of physics, astronomy, and human imagination. We began with a simple question about whether light could remember its past, and that question has led us through quantum mechanics, cosmology, consciousness, and the deepest philosophical questions about the nature of reality itself. The answer, as we have discovered, is both yes and no. Perfect photonic memory, the kind that would preserve complete historical records of every interaction and every moment of a photon's journey, appears to be forbidden by the fundamental laws of physics. Quantum mechanics, thermodynamics, and relativity conspire to ensure that information is constantly being lost, scrambled, and forgotten as the universe evolves forward in time. Yet light does remember, just not in the way we might have imagined. Every photon carries partial memories of its journey, encoded in properties like energy, polarization, and phase. These incomplete but precious fragments have revolutionized our understanding of the universe and continue to reveal new secrets about cosmic history. The cosmic microwave background radiation provides perhaps the most beautiful example of light's memory at work. These ancient photons have been traveling for almost 14 billion years, carrying within their properties the imprint of conditions in the early universe. The tiny temperature variations we measure in this radiation are fossils from a time when the universe was young, smooth, and very different from the complex cosmos we inhabit today. By decoding these photonic memories, astronomers have been able to determine the age of the universe, map the distribution of matter and energy, trace the formation of the first structures, and even detect gravitational waves from the earliest moments after the Big Bang. The cosmic microwave background is like a baby picture of the universe, preserved in light and delivered to our telescopes after an almost incomprehensibly long journey through space and time. Starlight carries its own forms of memory, recording the nuclear processes that occur in stellar cores and the conditions in stellar atmospheres. The spectral lines that astronomers observe are like fingerprints, revealing the chemical composition, temperature, magnetic fields, and motions of stars throughout the galaxy. These stellar memories have taught us how elements are created in nuclear furnaces and distributed throughout space by stellar winds and supernova explosions. The discovery of cosmological redshift represents one of the most profound examples of photonic memory changing our understanding of reality. When Edwin Hubble observed that distant galaxies appear redder than nearby ones, he was reading the memories of photons that had traveled through expanding space. This simple observation revealed that the universe is growing larger with time, and led to the realization that everything began in a cosmic event we now call the Big Bang. Gravitational lensing provides another spectacular demonstration of how light preserves information about its journey. When photons travel near massive objects, their paths are bent by the curvature of space-time, and this bending encodes information about the mass distribution they encountered. By studying lensing effects, astronomers can map the distribution of dark matter, weigh galaxies and galaxy clusters, and even search for planets around other stars. These examples show us that even without perfect memory, light serves as an extraordinarily detailed cosmic messenger. The partial memories carried by photons have enabled discoveries that would have seemed like magic to previous generations of humans. We can see back to the beginning of time, watch stars being born and dying, trace the evolution of galaxies, and search for signs of life around distant suns. But our exploration has also revealed the deeper reasons why perfect photonic memory cannot exist. The universe appears to be designed to forget, with information constantly being lost to decoherence, dissipated as heat, and scrambled by chaotic interactions. This forgetting is not a limitation or a flaw in the design of reality. It may be an essential feature that allows the universe to continue evolving and creating new complexity. Perfect memory would require fighting against the natural tendency toward increasing entropy, the second law of thermodynamics that gives time its arrow and distinguishes past from future. If every interaction were perfectly preserved, the universe might become trapped in an ever-growing archive of its own history, unable to move forward into genuinely new states. The quantum mechanical nature of reality imposes fundamental limits on information storage and retrieval that seem to be built into the logical structure of physics itself. The uncertainty principle, the no-cloning theorem, and the measurement problem all conspire to prevent the kind of perfect information preservation that photonic memory would require. Yet our journey has also taken us to the frontiers of theoretical physics, where speculative ideas about quantum entanglement, holographic principles, and exotic space-time geometries suggest that enhanced photonic memory might be possible under special circumstances. While these ideas remain unproven and highly speculative, they remind us that our understanding of fundamental limits is still evolving. The social and philosophical implications we explored reveal how profoundly perfect photonic memory would transform human existence. The elimination of privacy, the end of historical uncertainty, and the transformation of our relationship with time would create a world almost unrecognizable from our current experience. These thought experiments help us appreciate the value of forgetting, mystery, and the fleeting nature of experience in our actual lives. Perhaps the most important insight from our exploration is the recognition that light already serves as the universe's archivist, preserving enough information to tell us remarkable stories about cosmic history while maintaining enough mystery to keep the future open. The partial memories carried by photons strike a balance between information preservation and the forward flow of time that may be essential for the continued evolution of complexity and consciousness. Every time we look up at the night sky, we are reading the photonic archives of the universe. The light from each star carries information about nuclear processes that occurred millions or billions of years ago. The faint glow of distant galaxies tells us about cosmic evolution on the larger scales. Even the darkness between the stars carries information, revealing regions where matter is sparse and space is relatively empty. Modern astronomy is essentially the art of reading these photonic memories and interpreting the stories they tell. Each new telescope and detector gives us better access to the cosmic archive, allowing us to read older and more distant photonic messages. The James Webb Space Telescope, for example, can detect infrared light from galaxies so distant that we see them as they were when the universe was less than 1 billion years old. Future developments in quantum technology might give us even better tools for reading photonic memories. Quantum sensors and quantum information processing could potentially extract more information from individual photons than current technology allows. We might discover new ways to decode the partial memories that light already carries, revealing cosmic stories that are currently beyond our reach. The search for enhanced photonic memory also connects to broader questions about the nature of information, consciousness, and physical reality. If the universe is fundamentally an information processing system, as some physicists suggest, then understanding how information is stored and transmitted in photonic systems could provide insights into the deepest workings of reality itself. The question of whether photons could have memory has led us through some of the most profound concepts in modern science. We have explored the quantum nature of light, the expansion of the universe, the formation of galaxies and stars, the limits of information theory, and the philosophical implications of perfect knowledge. This journey illustrates how a single imaginative question can illuminate connections between seemingly disparate areas of human knowledge. As we conclude our exploration, it is worth remembering that the photons reaching your eyes as you read these final words are themselves carriers of memory. They preserve information about the surface they reflected from, the lighting conditions in your environment, and the electromagnetic state of the space through which they traveled. While they cannot tell you the complete history of their journey, they carry enough information to allow you to see and understand the